So this presentation is on measures of dispersion. It's about finding the quartiles and the interquartile range. There'll be a couple of other videos also about measures of dispersion, different aspects of that. This corresponds to Module 4 of the OLI textbook and Module 4, Topic 13 in the workbook. So a reminder about the difference between a sample and a population. We'll use a story in this particular presentation in which the population that we want to study is the set of all the oak trees in the Stanislaus National Forest. So each individual member of the population is one oak tree. And the variable that we intend to measure for each individual tree is the tree's diameter in inches at chest height. But there are too many trees in the forest for us to measure every one of them. So we get a representative sample of just 27 randomly selected trees. Now, we want to summarize the distribution of the diameters of the trees by finding some population parameters. These parameters in this case are the quartiles. These are numbers Q1, Q2, Q3 for the population, such that 25% of all the trees in the whole forest, 25% of the population, have a diameter less than Q1. And 50% have a diameter less than Q2. And 75% have a diameter less than Q3. So each one of these Q1, Q2, Q3 numbers, each one of those is a diameter. It's some number of inches. And we're trying to break the whole population up into 4 equal groups. The trees below Q1, the trees between Q1 and Q2, the trees between Q2 and Q3, and then the ones above Q3. So that's 4 different groups of equal size. 25%, or 1/4, of all the trees belong to each of the 4 groups, and that's why we call it quartiles instead of quintiles or percentiles or deciles. Okay. Now, we're stuck because of the millions of trees in the forest. We cannot measure them all. And that's often going to be the case when we're trying to estimate a population parameter. We will not be able to find it exactly. That's why we use the word estimate, meaning we try to get close, but we cannot find it exactly because we do not have access to all of the individuals in the population. So the idea in statistics is that sometimes we can use a sample, a small subset of the population, to get an estimate for a population parameter. So we plan to find some numbers for the sample, a Q1, Q2, and Q3 for the sample. In the previous slide, you see I was denoting these Q1 pop and Q2 pop and Q3 pop for the population, but now I've dropped off the subscript pop, and without the subscript now I'm not talking about the whole population. Now I'm talking about just some randomly selected trees, a small subset of the population in our sample. And so we want to cut our sample up into 4 equal groups, just like we would have done for the whole population. And we hope that the sample quartiles, each of these Q's, a number of inches, will be close to the corresponding population quartiles. And it's a probability problem that we'll address We'll do it with the mean later in the semester. It's the same kind of thing with all the statistics and parameters. It's a probability question to determine how likely or how close are the statistics likely to be to the parameters. So here's a sample of 27 randomly selected oak trees. This is the same data set that appears in the appendix of your workbook and also in the spreadsheet of data for the class. And we're going to find sample quartiles, trying to divide this sample into 4 equal groups. This is a sample of 27 oak trees. And we'd like to divide it into 4 equal groups. Same number of individuals in each of the 4 groups, and of course we're stuck because 27 is not divisible by 4. You can't divide it into exactly 4 equal groups. So the idea is to, we'll go in between 2 of these numbers some way and try to end up with a sample Q1 that we think might be close to the population Q1. With the millions of trees, it would be easy to divide into 4 groups that are 4 equal groups, or close enough to equal when you have that many. If you're off by 1, it doesn't matter. But here, because the sample is small, what you do with the guys that don't fit into equal groups makes a difference. Okay. Now there are a variety of different schemes for doing this, and they all have their problems. They all get better and approach the true population quartile if the sample gets big enough. But when the sample is small, every method for doing this is not quite perfect, and that's why there are half a dozen different methods. I'm going to talk about 2 of the methods. So this is Moore's method from his textbook, and it's also what seems to be implemented on the TI-84 calculator, seems to produce the same result as this. So what you do, we find Q2 first. It's the easiest one to find, and then we'll find the other ones after. So the second quartile, or the median, the guy where 50% of the individuals are above and 50% are below. Moore's method for finding that is, since we have an odd number, we have 27 oak trees. If you do the 27, the n, the sample size, plus 1, that's 28. N plus 1 is 28, and then you divide that by 2, you get 14. And so, according to Moore's method, the second quartile would be X14 for our example. So there's an odd number, and if you have like 27 oak trees, then there are 13 guys in the bottom half, trees in the bottom half, and then 13 trees in the top half, but tree number 14 is right in the middle. And so the diameter of the 14th tree, X14, diameter of the 14th tree, that would be the median. And then to get Q1, you just put a circle around all the data that are to the left of the median. You've sorted them out in order from the smallest up to the biggest tree, so the guy in the middle is middle-sized diameter. You take all the guys to the left of that in your list, all the smaller trees, and you find their median again. You find the middle of the bottom half, and that's your first quartile. And similarly, you find the median of the top half, and that's your third quartile. Okay. And then let me go on and demonstrate this with an example, and I'll come back to Triola's method in just a second. So here's our 27 trees, the sample size, the little n, equals 27. That's an odd number. So the second quartile is the guy in the middle here at position 14. You see I is the index of the tree. Like if I equals 1, that means tree number 1. And if I, the little I, equals 2, that means tree number 2. And so I equals 14 is referring to the 14th tree in order. And then, oh, that's a mistake right there. I've got to fix my... That's important. That's easy to mess up. You see, I is the tree number 14. X14 is the 4.9 inches that's the diameter of tree 14. The X with a subscript on it here is the diameter, and that's the quartile, 4.90 inches. You include one extra digit beyond the raw data, and you include the units of measurement. Now, there are 13 trees to the left of the median. And we're going to find the median of those 13 trees, and that's going to be Q1. So how do you find the midpoint of the 13 trees? You do 13 plus 1, that's 14. Divided by 2, that's 7. So tree number 7 is the tree in the middle. His diameter is 3 inches, so Q1 is X7, that's 3 inches. And you do the same thing for the 13 trees that are above the median, the 7th one of them, so that's 15, 16, 17, 18, 19, 20, 21. I've counted 7 trees up from the median to get the median of the top half, 6.50 inches. So that's how you get Moore's quartiles. And then for Triola's quartiles, it's a little complicated. There's a function in Excel that does this. I'll do another video at some point about getting sample statistics using Excel. I'll show you how to use this function. But what it does is you divide the sample size by 4. And so to find Q1, what you do is you look at the whole number part of n over 4. So you do the 27 divided by 4, and you get, let's see, 6 and 3/4, 6.75. So you get the 6th number in your list, and then you go 3/4 or 0.75, 75% of the distance between X6 and the next guy up. So it's called linear interpolation. It's just, you didn't hit right on the 6th guy in your list. You did not hit right on the 7th guy in your list. You hit somewhere in between. You hit at 6.75. So you go 3/4 of the distance towards the guy on the top. You're above X6, but you're below X7. You made it 3/4 of the way up to X7. And so that's how you find it. So to find the 3rd quartile, you divide by 4 and multiply by 3. And then you get the same deal again. You wind up not at a whole number, you end up at a whole number s plus some fraction. So you go up to xs, and then a little fraction of the distance up towards the next one in the list, xs plus 1. Then you can get Excel to do that arithmetic for you. There's several other schemes. They all have their issues, but they get better as the sample size grows larger. And then you get probability questions about how close are they likely to be to the true population quartiles. And that's just about it for this topic.